Hello everyone, welcome back to Daily Keen Cuts. Today we'll be taking a look at problems B2 to B4 from the Putnam 2023. These are really interesting problems, so without further ado, let us take a look at what these problems are. For problem B2, we have a short and succinct number theory problem. So let's take a look at what this problem says. For each positive integer n, let kn be the number of ones in the binary representation of 2023 times n. What is the minimum value of kn? Let's digest this problem a little. Essentially, suppose this is the binary representation of some number, then this number is basically given by 2 to the power of 0 plus 2 to the power of 2 plus 2 to the power of 5. So what this question really wants is for us to look at multiples of 2023. And we want to find some multiple such that, well, when we write it as the sum of distinct powers of 2, it uses as little terms as possible. And of course, we don't have to find the actual multiple, we just need to know what is the minimum number of terms that's needed to produce a multiple of 2023. So if you'd like to give this problem a go, I will encourage you to pause the video and try it out yourself. But if you are just here to enjoy the solution, let us take a look at what the solution is. So the very first question you might ask yourself is, let's start with the most extreme case possible. Is it possible for us to have kn equals to 1? So if kn equals to 1, this means I have 2023n being a power of 2 itself. But with a bit of thinking, you will realize that this is not possible because 2023 is basically 7 times 17 squared, right? 7 times 17 squared times n cannot be a power of 2 because we have 7 as a prime factor over here. So a power of 2 will not have 7 in it as a prime divisor. So this is definitely not possible. Well, how about kn equals to 2? So this time we have 2023n as a sum of 2 powers of 2, or rather 2 distinct powers of 2. Now, you can think about this possibility along the same lines, namely, well, I do know that 2023n must be divisible by 7. So is it possible for me to even have sum of 2 powers of 2 giving something that is divisible by 7? Well, it turns out that if we look at powers of 2 under mod 7, we have 1, 2, 4, and then it repeats itself because 4 times 2 is 8, which is 1 mod 7. So these are the only possibilities for the powers of 2 after you take mod 7. This means you can never find the sum of 2 powers of 2 that is divisible by 7. You just go through all the combinations of taking 2 of the terms here. So this again tells us that kn equals 2 is not possible. Well, how about kn equals 3? Well, this time, if you try to think about it, well, we have 3 terms to play with, 3 powers of 2 to play with, and it seems now to be more plausible that we can pick our terms wisely so that we get multiple of 7 as well as multiple of 17 squared, which should then give us a multiple of 2023. So let's try and construct a solution where kn equals 3 and see if we reach a contradiction or we end up with a solution. So what we want here is 3 distinct powers of 2. They add up to a multiple of 2023. Okay, so, well, we can make one simplification first. Without loss of generality, actually we can focus on the case where we know c equals to 0. Why is it so? Well, if we have a solution involving a, b, and c, we can take out the common factor of 2 to the power of c out. I assume c is the smallest here. So when we take out 2 to the power of c, in order for this to be a valid solution, n must also be divisible by 2 to the power of c. So I can divide 2 to the power of c on both sides, and then I have I replace the a minus c by a and b minus c by a, and then I have this expression instead. So in other words, for any solution here, I can always convert it to a solution where c equals to 0. So let us just focus on the case where we already know c equals 0 and see if we can find a valid solution. So now this greatly simplifies our life because we only need to fiddle with 2 possibilities. Okay, so as we have reasoned before, we need to make sure that this sum over here is divisible by 7 and is divisible by 17 squared, and then we'll be done. It will definitely be divisible by 2023. So the question is, can we choose a bigger than b bigger than 0 such that 7 divides this and 289 divides this? So let's start with 7. If we look at the powers of 2 under mod 7, as we have seen before, it repeats after a cycle of 3, so it's 1, 2, 4, 1, 2, 4, 1, 2, 4, and so on. Now, fortunately, we can choose 4 and 2 and plus 1 to it, and then we get a multiple of 7. So what this means is that, well, one possible way to achieve this criteria over here is to choose A such that is congruent to 2 mod 3 and B such that is congruent to 1 mod 3. So what about the second condition? Well, again, we can try and look at the powers of 2 and see if we can assemble two terms such that this condition is met. And very quickly, just going through the powers of 2, you realize that 256 plus 32 plus 1 is 289. So actually, if I choose A equals this and B equals this, then this condition will work. But of course, we want to have more options, right? So that we can also simultaneously meet these set of conditions here. So this means we have to find sort of like the cycle length, similar to what we did here, and then get a whole family of possible solutions. But we don't actually need the specific cycle length. All we need to know is a number such that the pattern here repeats itself. What I mean is this. So specifically, we know that the cycle length, which is also called the order, is going to divide pi of 17 squared. So this is one of the results from number theory, specifically Euler's theorem involving the Euler phi function. So what we know is that after pi 17 squared times going through this thing, the cycle will begin itself again. It's not a shorter cycle length, but it's a cycle length that will cause the pattern to repeat itself. So as long as we choose A is congruent to 8 mod pi 17 squared and B is congruent to 5 mod pi 17 squared, we will guarantee that 2 to the power of A is 256 mod 17 squared and 2 to the power of B is 32 mod 17 squared. So we now have two set of conditions that we can actually see if we can be met simultaneously. Well, firstly, let us simplify what pi 17 squared is by the formula for what the Euler phi function is. It is basically, if you have a prime power, is p minus 1 over p times that prime power. So this is just 16 times 17 and 16 times 17. So we need to meet these two conditions simultaneously. But fortunately, 3 and 16 times 17 are relatively prime. So by the Chinese remainder theorem, we can actually find A such that it meets this condition simultaneously and actually is a family of solutions under mod 3 times 16 times 17. So if you're not familiar with the Chinese remainder theorem, I'll encourage you to look it up as well. And same thing, we can find a value B that satisfies these two conditions simultaneously. So with that value of A and B, we meet these two conditions, and therefore this gives us a solution to this equation here. So in conclusion, the minimum value of Kn is equal to 3. So this application of Chinese remainder theorem reminds me of one of the footnotes that I found in one of my abstract algebra textbook, which says that allegedly a large number of Putnam problems can be solved by clever application of the Chinese remainder theorem. So I'm not sure how true this claim is, but actually there are a number of Putnam problems that are indeed solved with Chinese remainder theorem used in them, and this problem B2 is one of them. So do keep in mind about the Chinese remainder theorem. So that's all for problem B2. I hope you enjoyed this problem. I think it's a neat little number theory problem that can actually be suitable for IMO problem 1 or problem 4. Okay, let us now take a look at problem B3, which is actually another very nice problem. So we see that a sequence y1, y2, yk of real numbers is called zigzag if it basically goes up and down in the alternative fashion. So either k equals 1, where it's trivially just 1 point, or if y2 minus y1, y3 minus y2, yk minus 1 are non-zero and alternating in sign. So basically either up, down, up, or down, up, down, and so on. Okay, let x1, x2 dot xn be chosen independently from the uniform distribution of 0, 1. Let a of x1, x2 dot xn be the largest value of k for which there exists an increasing sequence of integers I1, I2 dot ik such that the x's are zigzag. Find the expected value of a for n greater than or equal to 2. So basically what it's saying is I choose n numbers uniformly at random from 0, 1. So let's say x1, x2 is like this. The value is along the y-axis. Then I want to let a be the largest subsequence of zigzag that I can find. So for example, I can take this, and this. That forms a zigzag sequence. In this case, I've chosen, I can't remember, 1, 2, 3, 4, 5, 6, 7, 8 points. And in this case, 8 is actually the longest subsequence that I can choose such that it's zigzag. So a over here will be 8. But of course, different values of x1 and xn will give different values of a. So I need to find the expected value of a. Okay. So once again, the key way to approach this problem is to first think about how do I compute a, let's say, when I've already picked x1 to xn. Is there an easy way to describe what the answer a would be given the values of x1 to xn? So let's take a look at one scenario where I've picked x1 to xn already and see how I can compute the value of a. Now firstly, without loss of generality, I'm going to assume that all the x1 to xn are pairwise not equal. Well, I can do that because the probability of two of them being equal is equal to 0. So I'm just going to ignore that case and assume all of them are distinct. Okay. Now, it's very useful to introduce a few terms. So I'm going to call a point a peak if its neighbors are either non-existent or smaller than it. So for example, this point, the neighbors are smaller than it. The immediate neighbors are smaller than it, so it's a peak. Now this point is immediate neighbors. This one is smaller than it, and on the other side, its neighbor is non-existent. So again, this is also considered a peak. Now conversely, I'm going to call a point a trough if its neighbors are either non-existent or strictly bigger than it. So again, this point is a trough because its neighbors are strictly bigger than it, and this side is a trough because its neighbor, this side is non-existent and this side is strictly bigger. So this point, for example, will be neither a peak nor trough because one of its neighbor is smaller while the other neighbor is bigger. Now, one thing to note with this definition is that the endpoints x1 and xn will definitely be either a peak or trough. Okay. Now, why do I bother with introducing the terms peak and trough? Because they will play an important role in our proof. Now, the first thing we check, and I think it's quite easy to motivate this claim, which is that selecting all peaks and troughs will give a zigzag sequence. So in this case, if I go here, I indeed get a zigzag sequence. And it's not hard to check. So moving from a peak to a trough will definitely be decreasing, and from a trough to peak is increasing, and you can't have two peaks in a row, and so on. So I'll leave this simple check to you to work out, but I'll focus more on the interesting part of the proof. So let's say you already checked that selecting all peaks and troughs give a zigzag sequence. Why do we bother with this part? So it turns out that selecting all peaks and troughs actually gives the largest value of k. Now, I'm not saying that any path with the largest value of k must be formed by selecting all peaks and troughs, but selecting all peaks and troughs is one possible way to get the longest subsequence of zigzag. So let's prove this claim. So the proof is quite easy to motivate as well. It's quite a standard technique. So what we do is, let's start with a selection of points that gives the largest value of k. We'll show that we can convert this selection into a selection that involves all peaks and troughs, but the value of k is unchanged. So in that case, this shows that selecting all peaks and troughs actually gives the largest value of k. How do we convert this selected path into all peaks and troughs? Well, we do this step by step. So whenever there's a selected point V that is neither peak or trough, what I'm going to do is I'm going to replace this with a peak or a trough. okay, that has not been selected before. So if this point is neither peak nor trough, it actually lies on the interior of an increasing or decreasing segment. So by segment, I mean the collection of points between from a peak to the next trough, or from the trough to the next peak. Okay, so in this case, it's trough to the next peak, so it's an increasing segment, but it can also be on a decreasing segment. Now I'm going to argue without loss of generality that we are on an increasing segment. The argument for decreasing segment is completely analogous. So what should we do with this point being on an increasing segment? Now, if V is a trough among selected points, then I claim that we can change V to the trough of its segment. Well, let's follow this argument closely. So V is a trough among selected points, so the point immediately before that is larger than V, okay? Larger than the value of V. This means that the points to the left of V all the way down to the trough itself is actually not selected, because this is larger than V, whereas going left we are going downwards until the trough. So all this cannot be selected, which means it's perfectly valid for me to change my selection of this point all the way to this trough over here. And in doing so, it still remains, the selected point still remains immediately after the previous selected point, and this next selected point remains immediately after the next selected point. Yeah, very important. I'm not arguing anything about to the right of the point. So it is possible that the next selected point is actually on the increasing segment, but to the right of it. I don't care about that, because I only care about moving this selected point to the left to the immediate next trough, immediate previous trough, okay? And I showed that this is possible. Now, conversely, if V is the peak among selected points, I'll go over the argument again to make it clear. We can again change V to the peak of its segment. So it's the exact same arguments. This selected point V being the peak among selected points means that the selected point immediately after that, okay, it could be non-existent, which also doesn't matter, or if it exists, it must be strictly lower than V. So this means all the points to the right of V along its segment, including the immediate next peak on the segment, are not selected at all. This means it's valid for me to move this point over to the peak of its segment, while retaining the order of the selected points being this to V to this. So hope that argument is clear. And what this argument shows is that my selected point, which was neither peak nor trough to begin with, is converted to a peak or a trough. And every time there's such a point that's not a peak or trough, I can always convert that. And I maintain the zigzag property of the path, which means that the value of k is unchanged. So this completes the proof of the claim. And more importantly, this tells us that we can easily describe the value of A now. The value of A is actually given by the number of peaks and troughs in the sequence. Okay, and from here we just need to find the expected value of the number of peaks and troughs. And when we are faced with a problem like this, it's actually quite a common technique to see if we can use the linearity of expectation and indicator trick. So this is very common in expectation questions. So you should always strive to work yourself towards being able to apply convert your expectation into the sum of indicator random variables. So in this case, I just simply define the indicator random variable of whether xi is a peak or trough, and then I sum it up, and this will give me the number of peaks and troughs. And then we apply the expectation, the linearity of expectation, and this gives us the sum of expected value of these indicator variables. And E of the indicator variable is just the probability. So this becomes the sum of probability that xi is a peak or trough. And this is actually quite easy to evaluate. Basically, if we focus on the point xi, okay, let's say xi is not x1 or xn, it's an interior point. So there's a point before that and a point after that. And what is the probability that xi is a peak or trough? Well, if we look at the magnitude, this is uniform 0, 1, uniform 0, 1, and uniform 0, 1. These 3 points after their peak, right, they will be a certain order to their size. This could be like smallest, the largest, and then in the middle, or middle, smallest, largest, or largest, middle, smallest, and so on. So there's actually 3 factorial permutations to the possible magnitude ordering among these 3 points, and each of the 3 factorial orderings have equal probability. So if we think about it, when for which magnitude ordering is xi a peak or a trough? Well, it's a peak or a trough when it's not smallest, middle, largest, or largest, middle, smallest. So this means that 4 of the 6 magnitude ordering will cause xi to be a peak or trough. So there's 2/3 probability that xi is a peak or trough. So this explains all the 2/3 over here. Now, as I mentioned earlier, x1 and xn is always going to be a peak or trough. So that's why the probability here is 1. So this means that I can simplify this. If I take all this as 2/3 and then I add on the extra 1/3 and 1/3 over here, the answer is simply 2/3 n plus 2/3. So that is all there is to problem B3. So it is actually quite a nice little problem which uses some combinatorial thinking, and then followed by a very standard application of the linearity expectation / indicator random variable trick that is very common for probability questions. So I hope you enjoyed problem B3. And now let us take a look at problem B4, which is another very fascinating problem. Now, this problem looks complicated and looks like an analysis problem at first, but after breaking down the problem, it will be converted to a very nice algebra / inequality problem. So let us take a look at this problem. For a non-negative integer n and strictly increasing sequence of real numbers t0 to tn, I define ft to be the corresponding real number function defined for t greater than or equal to t0 by the following properties. So there's a number of properties, I'll go through them slowly. Now, ft is continuous for t bigger than or equal to t0, so it's continuous for the whole function. And it's piecewise twice differentiable, so it's twice differentiable for all t bigger than t0 other than at t1 tn. So other than the points t1, t2, tn, t0 itself, in between they are all twice differentiable. So this means it's a piecewise twice differentiable function. Second, t0 equals half. Okay, that's straightforward enough. Third, the limit as t approach on the right side to tk of f prime of t equals 0 for all the special points. So this means for all the special points, right, if we approach from the right, the slope actually approaches 0. So that explains why in my picture all of these are starting off as like slope 0. Okay, now the last condition. For the last condition describes the shape of the curve in between the special points. So for k between 0 and n minus 1, we have f prime prime t equals k plus 1 for the values of t in between. So for example, over here, f prime prime is 1, over here, f prime prime is 2, and so on. And f prime prime is n plus 1 when t bigger than tn. So for tn onwards is f prime prime equals to n plus 1. So this is f prime prime equals 1, f prime prime equals 2, f prime prime equals n plus 1. So this set of conditions over here completely describes the function. It will look like this. Okay, now considering all choices of n and t0, t1, tn such that the gap from 1 tk from the previous one is at least 1, what is the least possible value of t for which f t0 plus t equals 2023? Okay, what does this mean? So basically, you get to choose the value of n, so the number of special points. You get to choose where to place your special points, subject to the condition that your special points are at least of distance 1 apart. I need to find, so based on whatever choices I have, I need to look at my different choices, right? what is the least possible value of t such that by the time this function climbs up a height of 2022.5, I cover as little distance here as possible. Okay, so 2023 is the final point, starts at 0.5. So I climb up a y distance of 2022.5. I want to choose my value of n as special point such that I use as little distance along the x-axis as possible. So that gives a very nice and clean interpretation of this problem that looks a bit complicated. So what is the trade-off over here that I can make? Well, so f prime prime is a constant, right? This means like starting at slope 0, the longer I let it run before I hit a special point, the faster will keep increasing. So I can definitely choose to make myself worse off by inserting a special point and start the slope again at 0. But why would I do that? Well, I will do that because when I insert a special point and start again, now my f prime prime is of a bigger value. I could start increasing my slope at a faster pace. Even the best is if I can very quickly reach f prime prime equals n plus 1 and the slope will go up very fast. But to do so, I have to keep restarting and resetting my slope. And so this is where the trade-off sort of happens, and you need to figure out, well, what is the best number of special points I should insert and where should I put my special points. Okay, let's now analyze the problem rigorously. But before that, I do want to make one very small technical point, which is that I'm going to assume that my value of t0 plus t is going to occur after tn, because if it doesn't occur after tn, like let's say it occurs here, then I can actually just ignore all the values of ignore t equals t2, t3, and so on. If it already achieved 2023 over here, then my real value of n is actually 1, right? So I'm just going to assume that I'm going to use all the way until actually tn itself before I hit the value of 2023. This will just make my notation simpler. Okay, now the first thing you'll want to investigate is, can I actually come up with a more explicit description of how this function behaves? So I have all these like piecewise function, right? And I know the f prime prime value. It will be less annoying if I can work with f itself than f prime prime. To describe the value of f, again, given f prime prime, there's certain initial conditions. So like the y value and the x value here will affect the expression for f. And to keep the expression simple, I'm just going to assume that the starting point over here is at coordinate 0, 0. Okay, so that I get a very clean expression of how to describe this function over here. So by just solving the differential equation directly, f prime is just ct, because the slope at the start is also 0, and then ft is just half ct squared. So why do I bother trying to find out this value of f, this expression for f? What I want to know is, if I go up by a certain amount, how much distance along the x direction do I need to traverse? So specifically, if let's say I gain a y height of half a, the value of half here is just to cancel the half here, then the distance along the x direction that I need to traverse is actually square root of a over c. So you can just very easily find this by setting this equals to half a and solving for t. So I get square root of a over c here. Now what does this mean? Let's go back to our diagram, our master diagram. So I need to cover a total height of 2022.5. But for each piece, where I cover half a, I need to travel a x distance of square root a over c. So if I distribute this height to begin between the different pieces, so I call it, let's say I want to gain height a1 here and a2 here, dot to a n plus 1 here, then the distance that I will need to travel is given by the sum of all these square root terms, and that will be my value of t. So I can completely rephrase this problem to say that I actually want to I want to define the values a1 to an plus 1 such that they sum to 4045, because half a the half A all sum to 2022.5. So all the A sum to 4045. And the x distance that will be covered is square root A1, square root A2 over 2, plus dot dot plus square root AN plus 1 over n plus 1. And the point is I want to minimize this x distance because that's the question, that's the point of the question. So I need to minimize this x distance subject to the y distance is covers 4045. And let's not forget that we need the special points to be placed at this distance 1 apart. So this means that the x distance covered for each piece of the curve must be at least 1. So I have square root ai over I is at least 1 for I from 1 to n. The last piece doesn't matter. There's no restriction on the last piece. Okay, so this problem is now converted to an inequality problem if we assume n is fixed. So if we assume n is fixed, then it becomes just a inequality problem over here that I explained on the previous slide. And how do we solve this inequality problem? Well, actually, it's not too difficult. You just need to think about try and explore the different extreme cases. So actually, it turns out that the objective is minimized if each of these distance here is 1, meaning each of the ai is equals to 1 for all I between 1 and n, and then you dump all the burden to the last term. So what's the proof of this? Well, suppose some ai is bigger than I. Then actually I can decrease ai by epsilon and increase an plus 1 by epsilon. It will therefore still achieve this. If I choose epsilon small enough, it will achieve this. And what happens is the objective function will actually decrease because I'm decreasing, let's say I'm decreasing this by epsilon and increase this by epsilon. This part is divided by 2, whereas this part is divided by n plus 1. So actually what I decrease here will outweigh what I've increased here. So the objective function will decrease. So that proves the claim. Although technically there's a small, very technical point about showing that the minimum will be achieved by some combination of points, but I'm just going to put that aside for now. Okay, so what have we achieved here? We know when the objective function is minimized, so let's plug that in. So when the objective function is minimized, we do know that all these terms are 1, 2, 3, and so on until n, and we need this equality to be achieved. So an plus 1 must be 4045 minus the sum of 1, 2, 3 until n. And so if we plug all this in, the objective itself at the minimum point would be 1 plus 1 plus 1 dot dot plus the last term, where the last term an plus 1 is given by this. So if I plug it in, then this will actually be the objective function at its minimum. So this greatly simplifies our problem to the following. Among all non-negative integers n, we need to minimize this. Why is this the equivalent problem? Well, because for a fixed n, this is the objective function that we get. So now we loosen out the last piece of choice that we have, which is we have the flexibility to choose n as well. So we need to choose n such that we end up minimizing this. So from here, this is a one variable problem. So it sounds like the problem is mostly done. Unfortunately, there's still one very annoying thing that we need to do, because solving this is actually rather annoying. So let's try to solve this problem. Now, turns out that most of the values of n will give something ugly here, but if you actually evaluate the first few values of n, you will eventually find that if you put n equals to 9, this objective function here gives you 9 plus this divided by 10 is 404.5 minus 4.5, which is square root 400, which is very nice, is 20. So the answer is 29 here. So it turns out that after n equals 9, this objective function will increase. So what I'm going to prove to you, I claim that 29 is the minimum answer here. So we want to show that for all values of n, this thing is at least 29. Well, obviously, if n is bigger than 29, then we are done. So I'm going to show that for n less than or equal to 29, we have the objective function is bigger than or equal to 29. So to do this, well, unfortunately, there's no clever trick. We just have to do brute force simplification. So we move n over, we square both sides. We expand and we clear denominators, and then we will get this factorized cubic over here. And unfortunately, this cannot be factorized nicely. So we have to argue through some non-beautiful methods. So one way to prove that this inequality is true is to observe that this is a quadratic that goes like down then up, right? And it is positive for n less than or equal to 8. So you can check it's positive for 8 at n equals 8. It's negative at n equals 10, which means that when it's coming down, it crosses the 0 somewhere between 8 and 10. So the quadratic is positive for n greater less than or equal to 8. And it's negative. Again, you can check when n equals to 29, it is this thing is still negative. So it's negative all the way between 10 to 29. So with this, we can show that together with the 9 minus n, this inequality is indeed, this part here is indeed more than or equal to 0. So that's all there is to problem B4. I find that the first part of the problem is really interesting, figuring out what the conditions mean. Converting it into the inequality problem was really cool. And then solving the inequality problem itself was also really cool. And then when we reach this part about minimizing this among the values of n, unfortunately, this isn't a really nice minimization problem. But nonetheless, I thought most of the problem is actually pretty cool. So I hope you enjoyed this problem as well. So that is all the problems that we'll be covering in today's video. If you have not checked out the previous video on paper A of 2023, do check out the video. If not, you can check out last year's Putnam questions as well. Do subscribe to the channel for more math videos. Thanks for watching and see you soon.